Okay, welcome to organic chemistry, last chapter, okay, chapter 7. We're going to talk about properties of functional groups in carbohydrates, lipids, amino acid, and proteins. Okay, for chapter 7, we're going to break into 3 weeks, okay, so part 1, part 2, and part 3, okay. So the first part, which is, we're going to talk about carbohydrates, okay. Then part 2, we're going to talk about lipids, and part 3, we're going to talk about amino acids and proteins. Okay, let's talk about part 1, okay, which is carbohydrates. So what are the objectives? The objectives includes the classification of carbohydrates as monosaccharides, disaccharides, or polysaccharides, understand the stereochemistry of carbohydrates, and identify the chiral carbons in carbohydrates, use Fischer projection to represent D and L compound, understand the physical and chemical properties of monosaccharides, disaccharides, and polysaccharides, and describe uses for important monosaccharide, disaccharide, and polysaccharides. Okay, so all these for chapter 7, it got closely, the molecules we're going to discuss are closely linked to the previous parts, yeah, which is the chapter 6, chapter 5, as well as chapter 3, okay. So basically chapter 3 to chapter 6, all these will be used to link to chapter 7. Whereas for chapter 3 to 6, you're going to use the chapter 1 and chapter 2 link to them, okay. So more or less you will see some of the overlaps, okay. So that is basically we are tying it down to the 3 groups of the macromolecules, the carbohydrates, lipids, and amino acids and proteins that is very commonly found in the food components, yeah. Okay, let's look at the first one, the classes of carbohydrates, yeah. So if you look at it, what are the origins of source of carbohydrates? If you look at it, all the carbohydrates are all actually not all, okay, most of the carbohydrates are originated from plant, yeah, okay. The reason is being that most of the plants, okay, are able to undergo photosynthesis, okay, which means that you're going to harvest the solar energy and convert the solar energy into glucose, okay. So whereas for animals, I can say that majority of the animals can't undergo photosynthesis, okay. So in that case, animals actually will consume plants to obtain the carbohydrates. So what are the importance of carbohydrates? There are 4 importance here. To provide energy, of course, okay, in the form of the starch, which is break down to glucose. Glucose will undergo the 4 steps in the biochemical pathways to synthesize the 8 molecules of ATP per glucose molecules, yeah. So to provide the energy, okay, in the form of ATP. To supply carbon for the synthesis of cell components, okay. So if the cells break down the carbohydrates, at the end you're going to get a carbon, okay. So the carbon will be used to for synthesize other cell components. To serve as a store form of chemical energy, okay. So the carbohydrates will be served as a chemical energy both for the plants and animals. For the plants, it will be stored as starch, whereas for animal, you're going to store as glycogen, okay. To form part of the structural element of some cells and tissues, okay. You can see that sometimes the cell components and the phospholipids, you see that they actually have carbohydrate moieties that actually attach together, okay. For example, it can be on the cell membrane, okay. It can be on the certain proteins, certain enzyme, and so forth, yeah. All carry a certain functions, of course. So what are the importance of carbohydrate in terms of economy? A lot of countries actually needed the carbohydrates to drive their economy. For example, in Australia, the wheat starch industry actually worth more than 7.5 billion per year, whereas in New Zealand, about the kiwi fruits is about 1 billion industry. Yeah. How about in Malaysia? Malaysia doesn't seem to be very focused on that, because Malaysia more or less they are focused on the palm oil instead. Okay. What are the functional groups found in carbohydrates? We can see actually there are hydroxyl groups. Actually, many hydroxyl group is present in the carbohydrate structures. Of course, with the carbonyl group as well. So you can see over here carbonyl and multiple hydroxyl, yeah, or what we call polyhydroxyl aldehyde or polyhydroxyl ketones. Okay, in this case, this one is a polyhydroxyl aldehyde, yeah. So for carbohydrates, actually we can classify into different classes based on their size. Okay, so we got monosaccharide, disaccharide, oligosaccharide, and polysaccharides. Okay, to be clear, the carbohydrates, if you want to break it down to a functional unit, the smallest is actually a monosaccharide. Okay, then if you got two monosaccharides joined together, it becomes disaccharides. Okay, through glycosidic bonds. If they are attached from about 3 to 10 units of monosaccharide joined together, okay, through glycosidic bonds, you're going to call it as an oligosaccharides. If you've got long chain of the monosaccharide joined together, it's going to become a polysaccharides. Yeah. So as I mentioned, the smallest units, a functional unit of carbohydrates, okay, is monosaccharides. Of course, if you break it down monosaccharides further, it can get into carbon skeletons. Yeah. So you can see here is a way of representing it. Okay, we got monosaccharides, two units of monosaccharide joined together through glycosidic bonds. Okay, form a disaccharide. About 3 to 10 units joined together through glycosidic bond. Okay, it's called oligosaccharides, and the polysaccharides is multiples here. It can be very, very long for polysaccharides. Later you see some examples. What is the name of linkages joining to monosaccharide units? I have mentioned many times already. It's called glycosidic bond. Yeah, glycosidic bond. So monosaccharide is the simplest form of carbohydrates. Okay, they are not able to be hydrolyzed to anything smaller. When I say not able to hydrolyze to anything smaller, we're talking about functional carbohydrates here. Of course, if you break it down further, you're going to get individual carbons. So mono refer to one. Okay, saccharide means to sweet. Yeah, so is mentioning about 1 unit of the sweet molecule. Okay. So the general formula for monosaccharide is CnH2nOn. Yeah. So usually if you're looking at like glucose is a 6 carbon unit, so it's going to be C6H12. Okay, 6 times 2 equal to 12, H12O6. Okay. Usually the monosaccharides range about 3 carbons to 9 carbons. The most common one is actually 6 carbon. Yeah, 6 carbon. Okay, looking at this, we can actually categorize. There are a number of ways to categorize that. One of the ways to categorize the monosaccharide is through the number of carbons. If it's 3 carbons, we call it trioses. Then 4 carbon, we call tetro. Tet means 4, tetroses. 5 carbon is pentoses. 6 carbon is hexoses. So any of the 6 carbon, monosaccharide, we call it a hexoses. Okay. So here you can see we got trioses, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. Okay, so 6 carbons are very common, and you can see from here one of the most common one they have is like glucose. Then we got like, for example, like the galactose. Okay, very, very common, galactose, glucose. All these are 6 carbon hexoses. Yeah, hexoses. In terms of this, because all these are the aldehyde variations, so we call it aldohexoses. Yeah, aldo stands for aldehyde. Of course, we got the ketone type. Yeah, okay, so in that case, we call it as a ketotrioses. Yeah, so just to refresh a bit, aldos, we have a carbonyl group at the end of the molecule. When we got the ketones, the carbonyl group will be somewhere in the middle of the carbohydrate structure. Yeah. Okay, so for carbohydrates, we have spoke about the stereochemistry. Yeah? Same thing, carbohydrates, they have stereochemistry as well. We got enantiomers, diastereomers as well. Okay, so just a quick refresh. What are enantiomers? Enantiomers are mirror image stereoisomers with the same molecular and structural formulas but different spatial arrangements. Okay, but for enantiomers, what we have is actually they have a pair of the mirror image. Okay, and to be more specific, is actually a non-superimposable mirror image to each other. Okay. So just to refresh a bit, how do you know that whether is it chiral carbons, okay, or whether is it a chiral molecules? The simplest way is to look at each of the carbohydrate, each of the carbon each of the carbon atoms, and looking whether is there any 4 different groups attached to it. Okay, so if there's a 4 different group attached to it, we call it as a chiral carbons. Okay, then from there, when a chiral carbon, it should be a chiral molecules. Okay, which means that when it's a chiral molecule, they have a pair of enantiomers. Okay, a pair of mirror image that is non-superimposable, we call it as a enantiomers. Okay, so while looking at it, we can see which are the chiral carbons. Okay, we need to look at each of it. In that case, you can see already here got the symmetry. So if this carbon, there is no chiral carbons here. Okay, this one has 3 same. Okay, so we rule out the end part already for this one because there's a plane of symmetry, so it's not a chiral carbon. Okay, so there's no chiral carbon in the example A. Whereas this carbon, no, already got 3H. How about this? No, this one no, and this one you got H1, 1 group, 2 group, 3 group, and 4 group. So this is a chiral carbon. Okay. So for carbohydrates, actually it can contain more than 1 chiral carbon. In this case, it's erythrose. Okay, so you can see from here, this one there is no chiral carbon because here got HH, 2 same one. Okay, here you got so 1 group, 2 group, 3 group, 4 group. So this is chiral carbon. Here 1 group, 2 group, 3 group, 4 group. Okay, it's a chiral carbon. Whereas this carbon is not a chiral carbon. The reason being that it's only got 3 groups here, 1 group, 2 groups, and 3 groups. Okay, so there are 2 chiral carbons, so which means that 2 to the power of 2 equal to 2 equal to 4. So we can actually draw 4 enantiomers out from this structure. Okay, or actually not enantiomers, we can draw 4 stereoisomers. From them we can pair it up whether is it the enantiomers or diastereomers. Okay, same like the stereoisomer chapter that we have spoke about. So if you're looking at the hexoses, which means that it has 6 carbon in there, then we need to look at one by one, see whether each of it whether is it a chiral carbons. So we look at this, number 1 is not because it got 3, 1, 2, 3. This one, there's 1 group, 2 group, 3 group, 4 group. So this one, yes. This one, 1 group, 2 group, 3 group, 4 group, yes. This one, 1 group, 2 group, 3 group, 4 group, yes. This one, 1, 2, 3, 4. So we already got 4 chiral carbon over here. Is this a chiral carbon? No, because it already got 2H, same one. Yeah. So the carbon number 6 and carbon number 1 is not chiral carbon. 2, 3, 4, 5 is a chiral carbon. In that case, so alright, this is basically what I have mentioned. So in this case, there are 4 chiral carbon to the power of 4. We can actually draw 16 stereoisomers. So you can draw 16 of them. You got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these are the 16 stereoisomers that you can draw from the hexoses, this structure. Okay. The variation is actually the location of the OH and H. You can see all here are aligned to the right side, and here you can see 1 left side, 3 right side, and so forth here. If you look closely, 16 of the stereoisomers actually each there are actually 8 pairs of enantiomers. Okay, so you can see from here, this and this actually is a pair of enantiomers. So if you put a mirror, you can see that here and here is actually a mirror image, a non-superimposable mirror image. Same goes with this and this. So here is a pair of enantiomers. Do we actually name it to differentiate it? We need to look at the hydroxyl groups, the second last hydroxyl groups. Okay, if the hydroxyl group is on the right side, we call it D. If it's on the left side, we call it as the L. So you can see from here, all these are the L, here all these are the D. Okay, so you can see from here, very common glucose. Okay, this stereoisomer is the one that is the most common in the world Earth. Yeah. Okay, so in this case, we usually, when we consume glucose, we consume D-glucose. Okay, the L-glucose is not that common. Yeah. Alright, you must be wondering, sir, so I can simply put this on left and right, okay, and call it as a D and L? Is no. Yeah. Actually, all this structure over here, which is a 2D representing of the structure molecule, is actually based on Fischer projection. Okay, so Fischer projection is a way to actually fix the location, whether is it on the right side or on the left side. Yeah. So when we're looking at the Fischer projection, usually we have a molecule. Okay, we have a molecule, okay, a 3D molecule. So from a 3D molecule, we want to determine whether is it D or L. Then we need to convert this through a Fischer projection. Okay, so once we have the molecule, then we will arrange it in such a way the most oxidized group is going to be on the top there, and then the OH and the H is going to facing you. Okay, and of course this one naturally will be facing back. Okay, once you have that molecule, again you can see here is actually it started with the original 3D molecules. We just arrange in such a way that the most oxidized group is facing top, okay, away from you, then this facing you. Okay, once you have this structure, then you imagine you press this structure onto a piece of paper. There you go. You can have a CHO, then you got your OH on the left side, H on the right side, and so forth. So in this case, is the OH is on the second last OH is on the left side, is called L. Okay, same thing, you arrange in the way that you press it down to the paper. If it's on the right side, then it is a D. Okay. Alright, so you can see from here, just to repeat what I have mentioned, draw a 3-dimensional structure representing the most oxidized carbons on the top there. Okay, then the others will be the vertical bonds will be directed away from you, and the horizontal one will be directed to you. Yeah, okay, vertical, horizontal. Once you have that, press it on the paper, then you got the OH fixed to the left side. Yeah, in this case, if it's on the left side, you call it L. Okay. Alright, so L and D glucose, yeah. Alright, so for multiple, just now was an example of just one. Okay, if you are multiple, as I mentioned previously in the previous sections, you look at the second last OH group. On the right is a D, on the left is L. Okay. So we look at the D and L system. The most abundant hexoses in the biological world in this earth, okay, is actually the D form. Yeah, we got D glucose, D galactose, and D fructose. Okay, let's look at some of the properties of the monosaccharides. Okay, this section we're going to link to our previous chapter. Yeah, so remember we have spoke about the aldehyde and ketones, okay, react with alcohol to form what we call the hemiacetal or hemiketal, correct? Okay, and this when we were mentioning, we are talking about the individual molecule. Yeah, what we have is an alcohol and the aldehyde. When they react, they form a hemiacetal. Then the hemiacetal form, right, is going to be unstable, which means that they're going to react with more alcohol to form a stable acetal. Correct? Okay. But in the case of the carbohydrates, in the carbohydrates, as you have seen before, they contain both the aldehyde, the carbonyl group, as well as the alcohol group. Okay. So in this case, right, when they react with each other, because these two groups are present in the same molecule, okay, because they are in the same molecule, when they react, they form a stable hemiacetal or a stable hemiketal, okay, because they cannot react with that, because it's a closed loop, so they are stable in that case, yeah. So for the carbohydrates, they can form a stable hemiacetal or stable ketals here. And it's very, very relevant in the structure of carbohydrates. I'm going to tell you later on. But at the moment, now let's concentrate in looking at how they react and how they actually form a cyclic structure. Yeah. So you can see from here, this is a D-glucose. Okay, 6 carbon, 1, 2, 3, 4, 5, 6. Okay, and then we have aldehyde groups, and then we got multiple hydroxyl groups. The one that cannot react is actually the one that we use it to determine the D and L, which is the second last the hydroxyl group. Okay, so the second last hydroxyl group is going to react with the carbonyl groups to form a cyclic form, a ring form. Okay, or a ring form. Okay, in this case we call it as a 6-member ring. We don't call it as a 6-carbon ring, because what you can see that in the structure, final structure, there is actually one which is an oxygen. Yeah, I see from here, whenever you form a hemiacetal or hemiketal, there's actually an oxygen in between. Okay, which is exactly same as what you have learned before. Yeah, just that the difference is that the carbonyl group and hydroxyl group is actually present in the same molecule. When they react to form a hemiacetal or hemiketal, it's a stable form. Yeah, which means that there's no further reaction required. Okay. So in this case, they're going to form a 6-member ring, as I mentioned. Is because there's an oxygen over here, which is the characteristic of hemiacetal or hemiketal. Then when they react, they will form, they will either having a hydroxyl group pointing top or pointing bottom. Okay, so whether pointing up or pointing bottom, it really depends on the reactions here. And the condition of where the glucose in, okay, because the pH, the temperature can actually affect which one to form, okay, either the beta or the alpha group. Okay, so beta is pointing up, the alpha is pointing down. Yeah, the rest of the OH group is actually all fixed. Yeah, all these are all fixed. Okay, it actually based on the location. If it's on the right side, it's pointing down, left side pointing up, okay, right side pointing down, and this one will be pointing up. Okay, so again, yeah, so you can see from here, same as this one. Second carbon, when the OH group pointing to the when it's on the right side, it will pointing down, left side top, right side bottom, this one on top. Okay. So if the OH group on top is formed, okay, the beta hydroxyl group, then we call it as a beta D-glucose. Okay, this one is called the alpha D-glucose. Okay, so this is this structure or 6-member ring is what we call a Harvard structure. So if you're looking at this, they can actually form either a alpha or the beta. As I mentioned before, it really depending on the condition where the glucose is present. It can be affected by the pH. It can be affected by the temperature. Okay. So normally when you consume those glucose or sucrose, they actually present in the ring form. Okay, they will be present in the ring form. The open chain form, which is this, is seldom present here. So again, normally those that you consume, okay, in the it can be in the sucrose or D-glucose we consume, Okay, it will be in the D form, of course, I mentioned, and it will be in the ring form. Okay, it will be in the ring form. Open chain form seldom occur, yeah, seldom occur. So it either be in this or this. Okay, again, depending on the situation or the condition of where the glucose is at. Okay, so it's very important for you to learn how to draw this here, because in the exam, I will be giving you this kind of structure and ask you to draw. If I ask you to draw a alpha D fructose, then you need to draw this OH group pointing downwards here, because it's alpha. Okay, so you must practice here. So in this case, for fructose, as you see, our aldehyde over here is at the second carbon. So of course, because it's located at the second carbon, the ring that is formed, although it's 6 carbon, 1, 2, 3, 4, 5, 6, okay, but because the carbonyl group is at the second carbon, so they form a smaller ring. In this case, they form a 5-member ring. Okay, whether it will be either the alpha or the beta D fructose. Yeah. So same thing, you can see from here, if the if this one, the third carbon is located on the right side, okay, it will be pointing up, right, left side it will be pointing up, right side pointing down, okay, and this one will be on top, yeah. Okay, so that one is fixated one, okay, based on the location of this. Alright, so this one, a cyclic form, if I give you this one is clearly, this is the hydroxyl group is pointing down, so this one will be the alpha groups. So if they ask you to draw a Howard structure in the beta form, Howard structure in the beta form, then you draw this in the pointing outward. The rest is all stay the same. Okay, you can see from here. When we ask alpha and beta, is only constant this. Okay. So over here, there are different what we call the level of sweetness, okay, what we call relative sweetness. We will be using table sugar, or what we call sucrose, as the benchmark. Yeah, so the sucrose or the table sugar, we benchmark at 1. So anything that is less sweet than sucrose is going to have a value smaller than 1. Those that is higher, then could be higher than 1. Yeah. So you can see from here, we got what we call invert sugar and fructose. Okay. So invert sugar is actually made from hydrolyzing sucrose. So this one is where the glucose and fructose are joined together to form sucrose. Is the sweetness level is 1, but once hydrolyzed, they got a mixture of glucose and fructose individual monosaccharide. As you can see from here, as we know, fructose is much more sweeter, like for example see over here. Okay, because of that, even though it's half 50-50%, okay, invert sugar is sweeter because the fructose is present as a monosaccharide. It's not tying down to the glucose. Yeah. Fructose, the individual one, you can see when it's 100% fructose, the sweetness level is very high. Yeah? That is why the industry love to use fructose. Yeah, it's because they only require smaller quantity to actually sweeten the product. Okay. So looking at the physical property of monosaccharides, because of a lot of OH group, it makes it extremely soluble, because each of the OH group can actually interact, forming hydrogen bonds with water molecule. Yeah. So we have also mentioned about this, the sugar alcohol. Okay, in the previous chapter, the carbohydrates can actually undergo the hydrogenation process. Okay. So after the carbonyl group under hydrogenation process or reduction or reducing the reaction, okay, what happens is that if you form a alcohol over here, you can see here, from a carbonyl to form an alcohol, and this is what we call a sugar alcohol. Yeah, sugar alcohol has very good properties and has been used at the industry a lot. Okay, as a low calorie sweeteners. Yeah. Because of change from a carbonyl group to the alcohol groups, although it still retains the sweetness, not as sweet as the original glucose. And because of the change, actually the bacteria as well as the human cannot absorb it to use it to produce energy. Okay, so that's why the confectionery industry, right, they love to use the sugar alcohol to sweeten their food, yeah, so that they can eat without worry about the calories, as well as they can use it on the chewing gum to refresh the mouth, okay, without providing more like sugars or glucose for the bacteria to grow in the mouth, yeah. Okay, let's talk about some of the examples of important monosaccharide, disaccharide, and polysaccharide, yeah. So for monosaccharide, the one that is most common and important, we have like glucose. Glucose is very important, abundantly in nature and present in the honey and fruits. Galactose, okay, is also very popular. So you can see from here the OH group is pointing upwards, okay. Glucose is pointing downwards, okay. Then we got fructose. Fructose is very, very popular nowadays, okay, because you just require a small quantity to provide very the high sweetness level, yeah. So it's an important sweetener because less fructose is needed than other sugar to achieve the same degree of sweetness, yeah. So you can see from here we got the beta, okay, pointing upwards, the fructose, yeah. Lactose, for the disaccharide we got like lactose, maltose, okay. So in this case, example is maltose, okay. Maltose is actually 2 units of glucose joined together, okay, through a glycosidic bond, yeah. So this bond form is a covalent bond, okay, and it's called the glycosidic bond. And this bond is called the alpha-1,4 glycosidic bond. So how do you know whether is it a 1,4? Then you look at the alpha-1,4, you look at the first the molecule. When they join together, if this one is pointing downwards, is alpha, okay. They connected at the first carbon, you can see from here, okay, alpha-1, okay, first carbon connected with carbon number 4 of the second monosaccharide, yeah, 1, 2, 3, 4. So this is alpha-1,4, yeah. Then we got another very, very important, which is table sugar, or what we call sucrose. In that case, we got alpha-1,2 glycosidic bond. You can see from here, pointing downwards, okay, carbon number 1 joined with the carbon number 2, forming a alpha-1,2 glycosidic bonds, yeah. And you can see that, realize that you can see, when they bonded, what happened is that they actually bond to the opening part. This part is the opening part, correct or not? When you form the hemiacetal or hemiketal, this is the part that will open or close, okay, open and close. But since this one is being tied down by the glycosidic bond, this no longer can be opened, okay. Opening for what? Opening for reactions. So since it's not available for reactions, that's why we call it as a non-reducing sugar, yeah, non-reducing sugar. So for the rest of it that we have mentioned, all the monosaccharide are reducing sugar, yeah, because the opening, this part can be open or closed, okay. This part can be open and closed for reactions, okay. Maltose, same thing as well, you can actually open, okay, so can undergo reactions, okay. So it's called reducing sugar. Whereas for disaccharide, it's the non-reducing because it's tied down, cannot open, so it cannot be reacted. The reaction we commonly talk about is basically the Maillard reaction, yeah. So Maillard reaction cannot occur when you use sucrose, okay. When you use glucose, all this, it can actually react, yeah. You might be a question that says, sir, if I use sucrose for baking, but I still notice there is actually a Maillard browning on the crust of the bread, okay. For those sucrose, do remember that it's actually not pure, yeah, it's not pure, okay. In the table sugar we use, some of the glucose, there will be some present, some of the glucose, some of the fructose in there, small amount, but it's sufficient to the important the Maillard reaction to form a brown crust, yeah, the bread crust. Okay, Then the other one that I have mentioned before is basically the formation of invert sugar. Yeah, so sucrose or table sugar, we have a mixture of 1-to-1 glucose glycosidic bond bonded with D-fructose. Yeah, okay. Because of that, okay, you can see from here, with the 1-fructose here. So because of that, okay, when you hydrolyze in the presence of acid and water, you actually form monosaccharide of glucose and fructose. Because of the presence of the fructose, it actually make the overall table sugar, hydrolyzed table sugar, sweeter. Okay, this is the same concept. They use it to cook acid-containing fruits or berries here, and then because when they cooking of these acid-containing fruits or berries, there will be, because of the presence of acid here, they will have a slight partial hydrolysis takes place, forming the invert sugar. That's why when you make jams, right, using acidic fruits, okay, like pineapple or pineapple, which is slightly the acidic, then you can make pineapple jams that is slightly sweeter, okay, because of these reactions here. Another important disaccharide is called lactose, okay, as I mentioned just now. Lactose is a principal sugar in milk, okay, and the milk, the lactose consists of D-galactopyranose here, bonded by beta-1,4 glycosidic bond. So what is bonded? You got a unit of galactose bonded with a glucose here. So you can see beta, this is a carbon number 1, okay, pointing outward, that's why it's beta, and then 1, 2, 3, 4, yeah. So beta 1, 4 glycosidic bonds. So lactose is a reducing sugar because you can see from here the opening is not bonded with the another unit. That's why it's a reducing sugar and is available for Maillard reactions. So you can see from here some of the important disaccharide, maltose, lactose, and sucrose. Yeah, these are the glycosidic linkage. Okay, those that are lactose intolerant actually is lack of the enzyme called lactase here, because when the person is lack of lactase, it cannot be hydrolyze the enzymatic hydrolyze here, not acid here, enzymatically hydrolyze lactose into glucose and the galactose. Yeah, so it cannot be hydrolyzed into glucose and galactose for entering into our cells to generate energy. Instead, it will be accumulated, okay, the lactose will be accumulated until your intestine, where your stomach bacteria will use it and break it and use it for energy. And because of the large quantity of lactose available in milk for the bacteria to undergo fermentations, that's why when they use it to fermentation, they produce a lot of carbon dioxide, sometimes acid as well. Yeah, that's why the person who are lactose intolerant, they felt a bit of bloated as well as gastric. Yeah, because the bacteria are enjoying consuming all the lactose that you just drank and convert into energy as well as carbon dioxide and acid. Yeah. So important polysaccharides, which is the larger ones, we got, for example, starch, glycogen, and cellulose here. Starch is in the plant storage of the glucose. Okay, the glucose are being joined together in a very, very long chain, okay, into starch and stored in the plant for usage later on. Yeah. Glycogen, same thing as well, is the glucose joined together to a long chain glycosidic bonds. Okay, and this one is present in our cell, our muscle cell, okay, as a reserve for energy. Cellulose basically is the cell wall of the plant. Yeah, same thing is made of glucose. Yeah, joined together through glycosidic bonds. So you will see over here, when they join together very, very large, they're going to be a very, very different type of properties. Yeah, you must realize that. Yeah, okay. You might be saying, sir, but then the polysaccharides, they have a large number of hydroxyl group. It should be soluble in water. Unfortunately, as the polysaccharides is very insoluble in water. Okay, Okay, there are some reasons here. When you're looking at these monosaccharides, the molecular weight is very, very low. Okay, polysaccharide is very, very high. You can see from here, the first distinction is that the taste. The monosaccharides like glucose is sweet in taste, but polysaccharide like starch is tasteless. You can put starch onto your tongue, it's tasteless because the molecule is so big, it cannot interact with your tongue. Okay, and hence it cannot be tasted. Okay, because it's too big to interact with your the tongue. Yeah. So whether is it soluble in water, glucose is soluble in water for sure. Okay, polysaccharide is insoluble in water because of large aggregations. Okay, when the polysaccharides, a lot of glucose unit join together to glycosylic bonds, very, very long. The hydroxyl group, because of the close proximity of each other, right, they're going to form hydrogen bond with each other. So which means that it's difficult for the water molecule to access to the polysaccharides, okay, because it cannot access. So cannot access is insoluble in water, yeah. The size of the particle small enough to pass through a membrane, very large cannot pass through membrane, yeah. Okay, there are two different two starch components that I'm going to talk about, amylose and amylopectins here. The percentage is only a reference, depending on the variety of the plant, okay, and also the source of the starch. The percentage is going to be different, yeah. The first one is basically amylose. Amylose is actually a straight chain, the carbohydrates here, okay, a straight chain polysaccharides, okay. So amylose is a straight chain. It can be very, very long, yeah, and the amylose can actually form, can actually interact with iodine to form a dark blue, the indicator, yeah, okay. So when you strip a bit of the iodine is about the greenish orangey, okay. So when you dip onto that, you're going to form dark blue. The more starch there, the darker it's going to be blue. Yeah, that's why here you see it's almost black color already. Yeah. Whereas the amylopectin of the starch components, okay, is going to be the branch chain. Yeah. So you can see from here is a branch chain. Okay, so it's a branch chain. It can be very, very big as well. So if you're looking at this, the starch component, okay, as I say, it can have a straight chain or a branch chain. Yeah. The percentage of it is very, very crucial. Okay, it plays a very important in determining what type of food product you can use. Because amylose, you can see the first distinction is that if you dissolve amylose, okay, same percentage as the amylopectin, you see that amylose actually is less viscous compared to amylopectin. Because amylopectin is like very branches, it's like broom like that. It causes very, very viscous. Okay. So the percentage is, you need to be careful of that, yeah. Okay, so I will this is the last slide, so I will end my lecture here. Okay, so if you got question, please ask in the Padlet. If you got no question, please indicate no question in the Padlet so that I can mark your attendance. Okay, thank you very much.